How many different ways can you reach your destination in a grid, no matter the twists and turns? Unique Paths is a Pattern Mastery 100 dynamic programming classic and a favorite at Google, Meta, and Amazon. Over 30% of candidates make mistakes with state transitions or grid boundaries. Master this and you'll unlock the foundation for nearly every grid-based DP problem in interviews. Let's solve unique paths using the basic approach, so you'll confidently tackle any path-counting DP challenge. Given an MXN grid, count the number of unique paths from the top left corner to the bottom right corner. You can only move right or down at each step. Integers m, n, grid dimensions. Integer, number of unique paths. Picture planning a robot's moves through a warehouse, or a delivery drone's flight plan over a grid city. Interviewers might ask, how would you count all possible routes if movement is restricted to right and down? What's tricky? You can't move diagonally or backward. Many candidates overcomplicate or forget edge cases for the first row/column. Dynamic programming and combinatorics both provide solutions. The robot can only arrive at a cell from above or left. For any cell, I, j, the number of ways to reach it is the sum of the ways to reach I1, j, and I, j1. Initialize the first row and first column to 1, only one way to reach each cell along the edge. Initialize a DP table of size MXN, fill first row and column with 1. For each cell not on the edge, dpij equals dpi1j plus dpij1. Return dpm1n1. Let's try to implement it using solution 1. Time complexity is OMN. Space complexity is OMN. This solution uses two-dimensional dynamic programming to count how many ways you can move from the top left corner of a grid to the bottom right corner if you can only move right or down. The main idea is simple. The number of ways to reach any cell is the sum of the ways to reach the cell above it and the cell to the left of it. Those are the only two places you could have come from. We store those counts in a DP table. We build it up row by row. And the final cell contains the answer. We start by creating a two-dimensional DP grid. Every cell in the first row is set to 1. Every cell in the first column is set to 1. That is because there is only one way to get there. You can only move straight right along the top row, or straight down along the left column. Next, we fill in the rest of the grid. For each cell, we add the number of ways from the cell above, and we add the number of ways from the cell to the left. Any path to the current cell must come from one of those two directions. It either comes down from above, or it comes right from the left. Once the table is filled, the bottom right corner contains the total number of unique paths from the start to the finish. So we return that value. And that's how this algorithm works. It first sets up a DP grid filled with ones for the easy edge paths. Then it fills the rest by summing paths from the top and left neighbors until the bottom right cell gives the final count. Efficient, simple, and elegant. Test case check. Unique paths using dynamic programming. Let's test our function using this input. M equals 3 and n equals 7. These numbers represent a grid with 3 rows and 7 columns, and we want to count how many unique ways a robot can move from the top left corner to the bottom right corner, moving only right or down. Here's why the solution works. We create a DP table where each cell dpij represents the number of unique paths to reach that position. The first row is all 1s because you can only move right. The first column is all 1s because you can only move down. Every other cell is the sum of the paths from the top and from the left. And that's exactly what our program outputs, 28. This matches the expected result, confirming that the DP grid was built correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all unique paths through the grid using dynamic programming, efficient, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is OM plus n. Space complexity is O1. This solution skips dynamic programming entirely. It uses a combinatorics shortcut. In an m by n grid, to reach the bottom right corner you must make a fixed number of moves. You must make exactly m-1 moves down. And you must make exactly n-1 moves right. You can make those moves in any order. So the problem becomes a counting question. How many different ways can we arrange these moves? That is a combinations problem. We choose where the down moves go among all moves. Or we choose where the right moves go among all moves. We compute that combination value using a loop. We multiply and divide carefully. That avoids huge factorials. First we translate the grid into a counting problem. N is the total number of moves you must make. That is because you are doing all rights and downs combined. Then K is the smaller of the two move counts. It is either the number of downs or the number of rights. Choosing the smaller one makes the computation faster and cleaner. Now we compute the combination value step by step instead of using factorials. Each loop step multiplies by a new numerator part. Then it divides by the current denominator part. This keeps the numbers manageable. And it gives the same final result as a full combination formula. It just avoids giant intermediate values. Because we are using division with floating point numbers, tiny rounding errors can appear. So we round the final value. That returns a clean integer count of unique paths. And that's how this algorithm works. It first turns the grid into a fixed sequence of right and down moves and sets up the combination parameters. Then it computes the number of move arrangements using a loop-based combination calculation to get the final count. Efficient, simple, and elegant. Test case check. Unique paths using combinatorics. Let's test our function using this input. M equals 3 and N equals 2. These numbers represent a grid with 3 rows and 2 columns, and we want to know how many unique paths lead from the top left corner to the bottom right corner, moving only down or right. Here's why the solution works. To reach the bottom right cell, the robot must make M1 equals 2 downward moves. N1 equals 1 rightward move. So the path is simply a combination of these moves. In total, the robot makes 2 plus 1 equals 3 moves, and we choose where the downward moves occur. And that's exactly what our program outputs, 3. This confirms that the combinatorial formula is computed correctly and matches the expected answer. Wrap up. So, our implementation is correct. The algorithm successfully uses combinations to calculate the number of unique grid paths, efficient, accurate, and reliable. Unique paths. Let's do a recap. So, we've just solved one of the most foundational dynamic programming challenges, unique paths. This problem isn't just about counting routes in a grid, it's about understanding how small decisions stack up into bigger patterns, a key skill that powers most grid-based DP problems you'll see in interviews. Breakdown recap. Conceptually, the task is simple. Find how many ways a robot can travel from the top left to the bottom right corner of a grid, moving only right or down. Every path you count builds from these 2 possible moves, and our goal is to track them systematically. Assess recap. We realized brute force would explode in complexity, so dynamic programming was the smart approach. The key insight was that every one cell's number of paths depends on just 2 previous cells, the one above it and the one to its left. Once we got that recurrence relation down, the problem became straightforward. Structure recap. We planned it like this. Start with a grid of path counts, initialize the first row and first column to 1 since there's only one way to move along the edges, and then fill the rest by summing the top and left cells. That pattern continues until the destination cell gives us the total number of paths. Implement recap. We implemented the logic cleanly, ran the solution on LeetCode, and everything executed perfectly. No syntax issues, no boundary errors. The DP table built up exactly as expected, and the output matched every test case. Check recap. After running multiple scenarios, all test cases passed successfully. The results lined up perfectly, even for edge cases like single row or single column grids. The logic worked efficiently and consistently. Closing insight. The big takeaway? Unique paths teaches the foundation of dynamic programming, breaking big problems into overlapping subproblems. Once you master this pattern, you'll start seeing the same logic in everything from grid traversal to robot movement to advanced combinatorial DP questions.